So we start off at the top here with our inputs, which are our x and y. We have our add and subtract button. So if the subtract is pressed, then the y value gets negated. So if the y value was a negative, it becomes a positive. If it was a positive, it becomes a negative. We then go in and we make a comparison with the exponent, and if we need to, we swap the exponent so the exponent of x is always greater than or equal to the exponent of y. So on the left hand side we have the near path, and on the right hand side we have the far path. So let's talk over the near path first of all. Now we only use the near path whenever we do a subtraction and there has been a cancellation. So in that case we take the mantissa value for x and the mantissa value for y. Now this cancellation will only occur whenever the exponent value is a value of 0 or a value of 1. So it means that the exponent will shift by either a factor of 0 or a factor of 1. So equivalently, it means that the mantissa of y will either shift by a factor of 0 or a factor of 1. So this is a possibility of a 1-bit shift, and we get the control of that shift dependent on the exponent value here. Now looking at these three blocks here within this yellow box, this provides us with the subtraction. But we said previously we want to subtract and ensure that we actually get a positive result, because the positive result in 2's complement is going to be the same as just a normal binary number. So we test the mantissa for x minus mantissa for y and mantissa for y minus mantissa for x, and depending on which one is positive, it will pass that through via this multiplexer. We then do the leading zero count and the shift. Now the leading zero count value will also be passed on to the exponent, so the exponent will decrease by this leading zero count, and it will give us the final exponent value here. And after this leading zero count and shift, the mantissa will then be passed out, and then we join the three together, that is, we concatenate them. So we take our sine, our exponent and our mantissa into just one block, and then it goes through this multiplexer, and there's a choice made by this multiplexer of the close path or the far path. Now sometimes you'll see it called the close path. The close path is just the near path, okay? So sometimes it's called close and sometimes it's called near. Now on the right hand side here, we're going to have all of the other options. So in all of the other options, we take a copy of the mantissa for x, because we're assuming that the mantissa for x is the largest value, because it have been swapped here in order to ensure that that is the case. We then go through either the addition or the subtraction algorithm, and again we get a control bit here which tells us which one we're going to be using. We also take a copy of the mantissa for y, and we have to shift it. So we're going to have to shift it by a factor of ex minus ey in order for us to do the addition or subtraction. We then pass the output here through the sticky bit. Now we've not talked about this before, so this is part of the rounding, but we'll get to this in a different video. And once we've done the adding or subtracting, we then get through the rounding and the normalization. We then output the value for our exponent, Ez, mantissa, Mz, and then we join on to the sine bit, which is given by Sz, so we concatenate these three together. We then pass this into the multiplexer, and again we make our choice. So if there has been a subtraction and the value of MR is less than 1, then we're going to choose this near or the close path. And if the opposite is true, that is, there hasn't been a cancellation, then we're going to use this far path here. And our output is going to come out at the bottom, which is x plus or minus y. So we can drop into the computer and then into the CPU, and then we can head across over to the floating point unit. Now we're interested in the adder and subtractor, which is here, and we'll drop into the top level. So you can see here we've got the same setup that we've seen through the rest of the video. So this is the dual path architecture with the near and the far path. You can see here there's a few extra items in that we didn't see in the schematic. So for example, we've got the addition of 1 for the hidden bit in the mantissa. We've got some stuff here on the special cases, and we've also got the splitter here, which splits the inputs into the sine, exponent, mantissa, and there's a few other sundry items. Now it's covered pretty much in the description over the first 5 minutes of the video. We've got the exponent or difference swap here. We've got our test to find out whether the value for our mantissa is going to be mx is greater or less than my in a potential swap. We've got a leading zero count here with a shift and the concatenation. And the other path here, we've got our shifter, we've got our adder subtractor, and we've got our rounding here with the sticky bit, and also the normalization and the concatenation here, and also the choice between the two paths. And finally, we've got the final part of the rounding. Now there's a lot more detail to this obviously than what we have covered in this video. Again, I say if you are interested, I do have a full course on this, and you're free to take that full course at any time. But we don't need to know all of these details in order for us to continue with the design of CPU 4. The circuitry for the floating point unit is really quite complex, and to look at it in detail really requires a separate course. Now we've finished with the multiplication and the addition and subtraction. The next one we're going to look at is the division and square root. So that's all for this video. Thank you for listening. I'll get you on the next video. Goodbye.